Here I am Vadel Sagar, and warm welcome to the part number 1 of the chapter number 2. So here we are uh, going for the next few days to the chapter number 2 about electrostatic potential and capacitance. The capacitance whole the concept we will see in a end of the zone of this chapter, but still that the electrostatic potential is the basic or main target word for the our few days discussions. Okay, so let's go without wasting time, and till that I can explain you that what is electrostatic potential. The potential word you come across in the many times in 11th class. Electrostatic word you may have introduced in the 12th first time in the first chapter. Electrostatic, electron, when the electro word comes, it means charges comes, and static means steady. Steady means charges are steady. Those studies in a physics done on the steady charge is called electrostatic field, and due to the steady charge it generate the potential is called electrostatic potential. Simplest language I can use for inputting the sense of electrostatic potential. Let's go without wasting time. What is potential energy? Because initiating the electrostatic potential, so you may have a you should have a clear cut idea what we learn in the 11th class. You cannot forget, because the 12th is the nothing but the standing, the 12th class is standing on the 11th class, so you may have very clear about the all 11th class studies. Okay, then let's define the potential energy. When an external force does work in taking a body one point to the another point, any body you have, don't see here, now I'm explaining. Any body you have, if you are applying the force on it, the body is moved from the one point to the another point. So you can able to see that, you can able to say that, you can also see that also and say that also, its body is moved, that work is happen on it, so it has store some potential energy. Suppose I have spring, if I compress it, it is I am applying force, it displaces also. So what force you are done on it, that much potential energy store on it. If you remove your force, that the potential will work on how much work is happened. Okay, that we know. This is nothing but the when an external force does work on taking place from point to another point, the force like a spring force, gravitational force, that works gets stored. Whatever work you are done gets stored as a potential energy in a body. That is the one of the way on which we can understand potential energy. Okay, now if we remove the force, what happened? The body moves gaining kinetic energy and either losing the equivalent amount of potential energy. So this is the best way you can understand by the spring example, and that I explained also. Okay, let's go ahead. The sum of kinetic energy and potential energy is the conserved. That conservations also we seen in many times, that you know. Okay, that is your conservation force. Generally for our present chapter scenario, spring force, gravitational force and coulomb force. Oh, till that whenever you come across with the conservation force, maybe gravitational force and spring force you may accept it, but the coulomb's law you just recently studied in first chapter of the 12th class, then the new addition or the new add terms is the coulomb force is also conservation force. Then you may got the question in your mind how it will be. So I can say coulomb force is exactly same as gravitational force, because it is here some electric sense is when charge is there, they are separated by some distance, they are attraction and repulsion. So there also in a gravitational force, two masses are there, they are attracting in nature, they are this force is the inverse square distance relationship. In a coulomb force also inverse square relationship. So what is the difference between them? No difference. So if the gravitational force is conserved, then the coulomb's, why not the coulomb's law also conserved. Thus, like the potential energy of the mass in a gravitational field, the potential energy of the masses whose in the gravitational field, we can define electron. The charge is also having its own potential, that is nothing but the electrostatic potential energy of a charges in a electrostatic field. So that things I can explain you in a very easiest sense. You have one charge, you have one proton, it has own electric field, that I can give the directly input in your brain, because you have a number of time the studies on this in the first chapter, right? Then you have one proton, it has electric field. This electric field has one region up to which it can do something, it can do the attraction repulsion according what charge is other fields and the comes into the picture of the scenario of the first proton what you have. Okay, then what okay, so that field region is called the electrostatic field. And that what potential energy, what if field on, what effect on the second charge, it's filled by the electrostatic energy, how energetically it will be react on it. So it depends on how strong electrostatic field it has. Now please read the like a potential energy in the mass scenario, it is called gravitational field due to the gravitational potential energy. Here also we have electrostatic field, it has electrostatic potential energy. Okay, now what is electrostatic field? E, that we seen also in first chapter very in detail in the equation scenario, and number of time we find also. But the basic understanding, one source charge you have q, capital Q, and at the some distance you have one another charge which is coin small q at the distance of r. Suppose it is initially it is r at that time, at that suppose any time. Now you are start to bringing this small q to the p point, it means comes towards the test charge from this, this is called source, this is called test charge, this is a source, from this it will be comes to it. The capital Q is that is at origin, we bring a test charge, this is called test charge because you are doing the testing on it. Test charge from the point r, point r to p against the repulsion force due to the charge q. Now when it feel the repulsion force, only when it will be both are same charges. If this is the positive, then this should be positive. Then when you are bringing the r to p, then this second or first also both are feeling the repulsive force because both are the same charges. Is it okay? So this is what I make a comment here, either the both are positive or the both are negative. Now what is it? I am going in detail of this same task. Two remarks may be made here. This is what we have. First remarks, we assume that the test charge q is very small, this is very small, and it does not disturb the original configuration. Like this is the same thing happen with the sun and earth. This is capital Q is the think about the sun, and then small q is a think about earth. Now earth is bringing from the earth orbit to the mercury's orbit, then what happened? It can able to drag the sun at the backside? No, because the sun is too huge and earth is too small compared to the sun. So here also if we have test charge is test charge is very small and the source charge is very highly compared to that one, so it will not disturb, it does not disturb the original configurations of the test charge or source charge q, capital Q. Okay, this is the first comment. What is the second can be in a bringing of this charge q? Suppose both are not that much different, sun and earth like, then it is like a earth and Jupiter, and like earth and Mars both are near equal. So in a bringing of charge q from r to p, this is a not kind of masses scenario, but what you understanding already have, that way I'm comparing so you can get an idea. Here very tiny particles, charges are very tiny particles, so I cannot compare to that one, but the scenario, the frame of reference for the imaginations comes into pictures, that's way. But here we have very tiny charges. Okay, so once you are bringing your from the r to p, we applying a force, Now if you want test charge from the R point to the P point, you have to do work on the charge Q. Obviously it cannot comes from the R point to the P point automatically. We have to apply force, and this force is F external, kept in your mind. Just enough, this much force. How much force you have to apply? This enough to counter or repel charge, because any two charge very far distance, they have repulsive force. If you are bringing towards its, if it is both are same charges, then the repulsion force is there. Now if you are applying force, applying force, if external applying force is not overcome the repulsion force, then test charge Q will not shift towards to the P. This is a basic understanding what we have. Is it okay? So that F external force, it should be enough which can overcome the repulsion force due to this charge. Now no need to overcome in the particular case, exactly same you are applying. So what is okay, slightly it will be shift. So counterpart to the electric repulsion force, exactly F external to the against the Fe, equal in magnitude and opposite in direction, because the F external this and repulsion is this. F external is this direction. That is very directional point of view. You are very clear. This means there is no net force applying on the charges. So acceleration is zero. It is moving with a constant velocity, but the acceleration is not there. It will not accelerate yourself or the test charge to continuously. No, because we are not exceeding that much force. Okay, this is called second remark can be possible in this case. Okay, now once it is reaches, once it pass, so yes, very easy to write these things. How much work we have to do, how much force we have to do, according how much it will shift. This is nothing but the work when a scenario R to P. It is a test charge is reaches to the R to P. This is a distance is integrations of the dr. We don't know how much it will be, and for the bringing the charge from the R point to the P point, we need to work WRP is equal to integrate over all distance R to P, whatever the force you have need to apply, which is F external time dr. This is a FD. W is equal to FD, that we are very easiest sense we have. Okay, as we are said in the second remark here, F external is nothing but the equal to the minus of Fe. Fe is nothing but the repulsive force, okay, which is applied by this party. That is your source. So this is, I can F external replaced by the minus of repulsive force Fe. This work done is against the electrostatic repulsion force gets stored into the potential energy of the system. Now if you are doing the against all the forces, you are applying external force on this charge, and this charge is applying a repulsive force, both are against each other, then one of the force is stored inside any of the charge in the potential energy. Okay, at every point in the electric field, because there is a charges are there, so the electric field is there. A particle with the Q possesses a certain electrostatic potential energy. It has original potential energy. This work done increases if you are doing the work on the test charge, which is small q. You are doing work is increase the potential energy, amount of potential energy difference between 2 point of R to P. And actual also potential energy is equal to mgh. It means as distance is varies, potential energy varies. If you are bringing your test charge at the R point to the P point, it means R point is having such a potential energy initially by the test charge. It's suppose any ur is symbolized as ur, because potential energy at the R. Now when you are bringing your test charge, that I made mistakes, I have to put that pictures in that slide also. If you have initially here, and now after that you are reduces to that point P also, then it has to be changed potential energy of the test charge. Then this is a UP. Then what is the difference between two potential energy? That much work you need to do. This is called work energy theorem. that we seen in 11th class also. So this is what we have. The potential energy difference is delta U is equal to UP minus UR. Obviously in this you are coming towards to in sense of another source which is a capital Q. So obviously potential will be increases. It's trying to stop because repulsion force are there. So the potential will be, potential energy is more in the sense of steady state. So when you are coming from the R point to the P point, you are feeling the repulsion force. It means trying to stop to your acceleration towards the point capital Q. So it will be your slow down. It means the potential energy, the UP will be more. So that's why I'm just taking the subtraction from the UP minus R, UR. Okay, and that is nothing but the work of R to P. Exactly that much work you need to do. That is called work energy theorem that we already seen also. You can read the remark also. Note here the displacement is an opposite sense to the electric force because electric force from the capital Q to this side, and your work done is happened from the opposite side. Hence the work done by the electric field is negative. So what work from this to this you are applying is WRP, and once the just this charge is coming towards this direction, this charge is also doing the work on the test charge is the minus WRP, equal and opposite. This is what minus WRP, equal and opposite. The two important comments also here, the conclusive points. One is, this is what we have, the depends only an initial. This is the difference of potential energy and the work what you find. It depends on initial and final energy of the charges. It means that the work done by an electrostatic field, work done by an electrostatic field is moving charge from the one point to the another point depends only on initial and final positions or the point, which is completely independent to the what path it takes. Now let me explain these things. Somewhere I have picture. Yes, don't see the what others in the front of it. So this charges comes from the R point to the P point. Whether it takes place in this way, whether it takes place in this way, it not matter which path is taking for the reaching from the R point to the P point, don't matter. Okay, this is what we seen in the conservations of the forces definition. This is our first remarks. The first remarks we get an idea whether it is okay, the test charges come from the R point to the P point in a whatever path it taking from the via Dharmaj, via Petla, via Borsad. It's not matter, I'm just reaching from my village to the P Chandras. That is important. That much displacement I made. This is the fundamental characteristics of the conservation force. That's why the electrostatic Coulomb's law is the conservation force, because it's independent to the path. And this is the way on which we can conclude it is a conservation force. Okay, this is the first remarks which is independent to the path. It is conservation force. Second remarks from the same, delta U is equal to subtractions of the potential energy of the respective places of R and P, which is nothing but the equivalent amount of the work you need to do. Is the defined potential energy difference of the physically nothing but the, it's nothing but the work, meaning clearly the potential energy so defined as underdetermined, so understand mine to within an additive constant that I am explaining you. What this means that actual value of the potential energy is not physically significant. Actually what potential energy we are not getting a 100% idea of it, but it is only the difference of potential energy has some significance. Potential energy, independent potential energy is not meaning, there is no meaning in physics. Difference of potential energy is having some meaning, which is called here, this is here difference, it has meaning, which is done by the difference of potential energy explained using the work scenario, and that we made here. And that is what the constants are coming with it, up plus alpha. We don't know, something is there, minus ur minus plus alpha, but the ultimately up minus ur only you will get. Difference between the 2 point charges, difference potential energy. A convenient choice is to have the electrostatic potential is energy 0 at infinity. with these choices if we take a point r as an infinity. Now whatever the point r, you have certain finite distance from the original q, you need to take r as infinity point. These points are very far to the your what original charge you have. Then your work you need to do is how much is w alpha p is equal to up minus u infinity. What in potential energy at infinite point is nothing but the up. So it is nothing but the fundamental definitions of potential energy. How much work you need to do, this much work you need to do for reaching the point charge from the infinite distance to the your finite region of the within the charge region is called potential energy. This is a very fundamental definitions what I represent in this is the one of the slide. How much work you need to do from bringing this point from the infinite distance to the p point is called potential energy. Potential energy of the vup. Okay, the provides us the definitions of potential energy of a charge q at a point, any point in infinite space. Potential energy of charge q at a point, the presence of field due to the any charge configuration is the work done by the, it's the work done by the external force in a bringing the charge q from the infinite distance to that point, which is nothing but the p point. Okay, this is the what the basic things we seen today for the required for the further discussions in the present chapter, chapter number 2. Thank you for the today's discussion.